I am going to read the chapter Dienes of Organic Chemistry from the book of Modern by Dr. J.M. Sehgal. Chapter 3 Dienes 3.1 Introduction. The alkadienes, or as they are most commonly known, the dienes, are unsaturated hydrocarbons containing two carbon-carbon double bonds per molecule. They have the general formula CnH2n-2 and are isomeric with alkynes. But the behavior of dienes and alkynes is quite different from each other. 3.2 Classification. Dienes are divided into three classes depending upon the arrangement of double bonds in the molecule. The three classes are A. Isolated dienes, C double bond CH, then CH2, then CH double bond C. The dienes in which double bonds are separated by more than one single bonds are known as isolated dienes. For example, 1,4-pentadiene, CH2 double bond CH2, CH2, CH double bond CH2, and 1,5-hexadiene. B. Cumulated dienes. The dienes in which the two double bonds are present between successive carbon atoms are called cumulated dienes or alkenes or cumulated cumulins. For example, 1,2-propadiene or allene, 1,2-propadiene or methylallene. C. Conjugated dienes. The dienes in which the double bonds are separated by a single bond are termed conjugated dienes. For example, 1,3-butadiene and 2,4-hexadiene. 3.3 Nomenclature. Cumulated dienes are commonly named as alkyl derivatives of allene. CH2 double bond C double bond CH2, which is the simplest member of this type of dienes. For example, methylallene and 1-ethyl 3-methylallene and 1,1-dimethyllallene. IUPAC nomenclature of all types of diene is similar to that of alkene except that the numeral if is added before the suffix "ene" to indicate the presence of two double bonds. For example, 1,2-propadiene, 1,2-butadiene, 1,3-butadiene, 5-methyl, 1,3-hexadiene. 1,5-heptadiene, 2,7-dimethyl, 2,5-octadiene. 3.4 Relative stabilities of dienes. It is interesting to note that difference in the relative locations of double bonds in the molecule causes appreciable difference in the relative stabilities of different classes of dienes. The data of heats of hydrogenation of alkenes and dienes clearly shows the conjugated diene are more stable than the non-conjugated ones. For a diene, the total heat of hydrogenation may be expected to the sum of the heats of hydrogenation of individual double bonds. This is found to be for non-conjugated dienes. For instance, the observed heat of hydrogenation of 1,4-pentadiene is 254.4 kJ per mole, while the expected value is 251 kJ per mole. But in case of conjugated dienes, this is the observed value are lesser than the anticipated values. For example, the actual heat of hydrogenation of 1,3-butadiene is 238.2 kJ per mole, which is 12.8 kJ lesser than the expected value. Similarly, the heat of hydrogenation of 1,3-pentadiene about 16.7 kJ lesser than the expected value. Now, two isomeric dienes which differ only in the relative location of double bonds, for example, 1,4-pentadiene and 1,3-pentadiene, give rise to the same alkene of hydrogenation. Still, if the conjugated diene involves lesser energy than the non-conjugated one, only means that the former contains lesser energy than the latter. In other words, conjugated diene system is more stable than non-conjugated diene system. The greater stability of conjugated dienes may be explained in terms of resonance or delocalization. 3.5 Structure of 1,3-butadiene. It has been stated above the conjugated dienes are more stable than non-conjugated dienes. The extra stability of conjugated dienes can be explained in terms of their structure as discussed below. Is considering the structure of 1,3-butadiene. 3.5.1 Resonance structure. Unlike non-conjugated dienes, conjugated dienes exist as resonance hybrid of various contributing structures. For instance, 1,3-butadiene is a resonance hybrid receiving contribution from many structures, the more important of which are CH2, double bond CH2, single bond CH, double bond CH2. Then CH2 positive bond with CH double bond CH bond with CH2 negative. And the third is CH2 negative single bond CH double bond CH single bond CH2 positive. It should be noted that structures second and third involves separation of charged particles. As such structure first, which do not involve any separation of charge, is the most stable and therefore the most important of all the contributing structures. The actual structure of butadiene is a resonance hybrid which lies somewhere in between the contributing structures but resembles the structures first more closely. This means that the bond between first C and second C or third C and fourth C is not pure double bond but quite close to it. Similarly, the bond between the fact that bond length between first C and second C or third C and fourth C is nearly the same as that of C double bond C, while the bond length between 2C and 3C is somewhere lesser than that of C single bond C. Thus, relatively greater stability of butadiene can be attributed to resonance, the resonance energy being responsible for the greater stability of other conjugated dienes. 3.5.2 Orbital structure. The orbital picture of conjugated dienes affords a better way of understanding the nature of bonds in conjugated dienes. For this purpose, let us again consider 1,3-butadiene as a typical case. Each of the 4 carbons of 1,3-butadiene uses 3 sp2 hybrid orbitals for the formation of the bonds and n unhybrid p orbitals for the formation of pi bonds. Shows p orbitals of the 4 carbon atoms of butadiene before the formation of pi bonds. Overlapping of p orbitals of first C with that of second C and of the p orbitals of third C and fourth C is shown in figure. However, if the 4 carbons and the hydrogens attached to them lie in the same plane, then the orbitals of 1C and 2C can also overlap as depicted in the figure. This means that there is an overlapping of p orbitals of 1C and 2C, 2C with 3C and 3C with 4C as shown in the figure. This results in the formation of pi molecular orbitals which covers all the 4 carbon atoms in the figure. As already examination of a pi molecular orbital which covers all the 4 carbon atoms. As already explained, such a molecular orbital which is spread over the nuclei of more than 2 atoms is known as a delocalized molecular orbital, and the electrons present in it are termed as delocalized electrons. As in case of normal or localized molecular orbitals, delocalized molecular orbitals also consist of 2 electron clouds, one lying above the plane of atom and the other lying below the plane. The presence of delocalized orbitals is supported by the fact that the bond lengths between any 2 adjacent carbon atoms in 1,3-butadiene neither corresponds to carbon-carbon single bond nor carbon-carbon double bond length. Thus, the greater stability of 1,3-butadiene is due to the presence of delocalized electrons, as each pair of delocalized electrons attracts and is attracted by 4 and not 2 nuclei. The same explanation also applies to other conjugated systems. More recently, it has been suggested that the greater stability of conjugated dienes is due to the variations in bond lengths and bond energies due to the particular hybrid states of carbon atom. 3.6 Methods of formations of dienes. Dienes are generally produced by suitable variations of the methods employed for the preparation of simple alkenes. The more commonly employed methods are given below. First, catalytic dehydrogenation of alkanes and alkenes. For example, 1,3-butadiene may be prepared by passing the vapors of N-butane over heated Cr2O3 and Al2O3 catalyst. CH3, CH2, CH2, CH3 on Cr2O3 or Al2O3 with heat, it gives CH2 double bond CH, single bond CH, double bond CH2 plus 2H2. 1,3-butadiene is also obtained by passing the vapors of 1-butene or 2-butene over heated nickel phosphate or calcium phosphate. Second, dehydrohalogenation of dihalogen derivatives. For example, on heating with alcohols potassium hydroxides, 1,3-dichloro-3-methylbutane gives isopropane. 3. Dehydration of diols in the presence of acids. For example, dehydration of 1,4-butadiene by heating in the presence of sulfuric acid or phosphoric acid results in the formation of 1,3-butadiene. 4. Pyrolysis of cycloalkenes. Retro-Diels reaction. For example, 1,3-butadiene can be prepared by passing the vapors of cyclohexene over heated nichrome, an alloy of nickel, chromium and iron. 3.7 Chemical reactions of dienes. The chemical properties of dienes are essentially due to the presence of two carbon-carbon double bonds in their molecules. Thus, non-conjugated dienes behave in exactly the same manner simple alkenes, except that the attacking reagent is consumed in twice the amount required for a double bond. In case of conjugated dienes, however, the properties of the double bonds are considerably modified due to the characteristic relative arrangement of double bonds. This relative arrangement enables the two double bonds to interact with each other so as to modify the behavior of the molecules as a whole. Thus, conjugated dienes are characterized by their greater stability and the occurrence 1,4 addition reactions. The important reactions of dienes are discussed below to illustrate their behavior. (3.7.1) Electrophilic addition reaction 1,2 and 1,4 addition reactions. Dienes undergo the usual electrophilic addition reaction shown by alkenes. However, due to the presence of two double bonds in the molecule of dienes, the total quantity of addendum is naturally 2 times the required of an alkene. The important electrophilic addition reactions are given below. First, addition of halogens. When treated with halogens, dienes react with 2 moles of halogens per mole of dienes to form tetrahalogen derivatives. For example, CH2 double bond CH single bond CH double bond CH2 plus 2Br2 gives CH2Br, CHBr, CHBr, CH2Br, that is 1, 2, 3, 4 tetrabromobutane. The really interesting point, however, is what happens when only one molecule of the addendum is made to react with 1 mole of diene. In such a case, the two double bonds of the conjugated diene act independently of each other and addition takes place across either the double bonds. For example, CH2 double bond, CH single bond, CH2 single bond, CH double bond, CH2, that is 1,4-pentadiene. When reacts with Br2, it becomes CH2Br, CHBr, CH2, CH double bond CH2, that is 4,5-dibromopentane. But a different situation prevails in case of conjugated dienes. To illustrate it, let us consider the addition of 1 mole of bromine to 1,3-butadiene. The products obtained consists of a mixture of 3,4-dibromo 1-butene and 1,4-dibromo 2-butene as shown below. The formation of 3,4-dibromo 1-butene is not surprising as it is the result of normal addition. also termed 1,2 addition, to adjacent carbon atoms linked by a double bond. But the formation of 1,4-dibromo-2-butene due to 1,4 addition, that is addition at terminal carbons of the conjugated system, appears to be unexpected. Mechanism of 1,2 and 1,4 addition conjugated dienes. To understand the occurrence of 1,2 and 1,4 addition reactions, let us examine the mechanism of addition of bromine to 1,3-butadiene. The reaction takes place in two steps, through the initial formation of allylic carbocation. First, formation of carbocation. As the bromine molecule approaches the dienes to get polarized, the positively polarized bromine adds to C1 to butadiene to form an allylic carbocation and a negative bromide ion. A primary carbocation, CH2 double bond CH, CHBr, CH2 positive, could also be formed by the initial addition of bromine to C2. But the ion A is formed in preference to this primary carbocation, as the former is not only a secondary but also an allylic cation, which is stabilized by resonance between structures A and B. The two contributing structures A and B differs from each other in the location of double bonds and of the positive charge. In the resonance hybrid of these structures, the positive charge is not localized on C2 or C4 but is spread over both as shown. Second, addition of bromide ion. It is clear that there are two positive charges centers in the cation which may be attacked by negative bromide ion in the second step of addition. Addition of bromide ion at C2 would give 1,2 addition product, while addition of bromide at C4 would give 1,4 addition product. Addition of halogen acids. 3. Addition of halogen acids to conjugated dienes is similar to the addition of halogens. Addition of 1 mole of halogen to acid to a conjugated diene gives rise to both 1,2 and 1,4 addition products. For example, 1,3-butadiene is converted into 3-chloro-1-butene and 1-chloro-2-butene. Mechanism. To start the reaction, a butadiene molecule abstracts a hydrogen ion from hydrogen chloride to form an allylic carbocation and a negative chloride ion. Initial addition of hydrogen ion could also take place at C2, giving a primary carbocation CH2 double bond CH, CH2, CH2 positive, but the ion is formed in preference to this primary carbocation, as the former is not only a secondary but also an allylic cation, which is stabilized by resonance between structures C and D. The resonance of hybrid of these contributing structures may be represented as shown below. Thus, there are two positive centers which may be attacked by negative chloride ions in the second step of addition. Addition of chloride ion at C2 would give 3-chloro-1-butene, that is 1,2 addition, while addition at C4 would give 1-chloro-2-butene, that is 1,4 addition. 3.7.2 Effect of temperature on 1,2 and 1,4 addition of conjugated dienes. It has been found that the ratio in which the 1,2 and 1,4 addition products are formed in a result of electrophilic addition to conjugated dienes is largely governed by temperature at which the reaction is carried out. Generally speaking, 1,2 addition product is formed preferentially at lower temperature and in non-polar solvents, while 1,4 addition products predominates at higher temperature and in polar solvents. For example, 1,3-butadiene is converted into 1,2 abducts 80%, 1,2 abducts 20%. Explanation of the effect of temperature on 1,2 and 1,4. The effect of temperature on 1,2 and 1,4 addition reactions may be attributed to the following reasons. First, E act leading to 1,2 addition products is less than the leading to 1,4 addition products. As such, 1,2 addition takes place more readily than 1,4 addition. However, 1,4 adduct once formed is more stable than 1,2 adduct. Second, both the addition products can undergo ionization, forming a common carbocation first. This leads to an equilibrium between two products and the carbocation as shown below. It may be noted that the carbocation first is the same as the intermediate carbocation forming during the first step of the reaction, that is CH2 double bond CH single bond CH double bond CH2 plus HBr is converted into CH3 CH CH CH2 plus Br. Since the energy difference between 1,2 adduct and carbocation 1 is lesser than between 1,4 adduct and the carbocation, ionization on 1,2 adduct takes place readily while that of 1,4 adduct takes place slowly. At lower temperatures, the ionization of products occur to a very small extent only so that the 1,2 adduct which is formed faster is the main product isolated. This means that the lower temperature is relative amounts of the two products obtained are in accordance with their relative rates of formation. In other words, the reaction is kinetically controlled. At high temperature, ionization becomes more important. The 1,2 adduct, which is thermodynamically less stable, readily ionizes, while the 1,4 adduct, although formed slowly, does not ionize readily. As such, the 1,4 adduct is present in large quantities when the equilibrium is reached, and therefore the main product obtained. In other words, at high temperature, the reaction is thermodynamically controlled. Second, free radical addition reaction. Like simple alkenes, conjugated dienes also undergo certain free radical addition reactions in the presence of suitable organic peroxides. Moreover, the addition of free radicals can also lead to the formation of both 1,2 and 1,4 addition products. For example, CH2 double bond CH single bond CH double bond CH2 plus BrCCl3. In presence of peroxide, it gives 1,2 addition product and 1,4 addition product. Mechanism. The mechanism of free radical additions such as that given above may be summarized as follows. First, peroxide to radical, then radical to BrCCl3 converted into radical bond Br plus CCl3 radical. The resonance hybrid of E and F may be depicted. It may be noted that the alkyl free radical formed in step 3 is the resonance hybrid of structures E and F. In the resonance hybrid, the odd electrons is distributed between 2C and 4C. As a result, this allyl free radical can form either 1,2 or 1,4 addition products by abstracting a bromine atom from another molecule of BrCCl3. The newly formed CCl3 radical then carries on the chain process. It is interesting to note that the free radical addition to conjugated dienes proceeds at much faster rate than similar reactions with simple alkenes, even though conjugated dienes are themselves more stable than simple alkenes. This unexpected reactivity of conjugated dienes towards free radical addition is attributed to much great stability of the intermediate allyl free radical as compared with the intermediate free radical formed from simple alkenes. Therefore, the net E-act for the formation of intermediate allyl free radical is lesser than E-act for the formation of intermediate free radical in case of simple alkenes. As such, the free radical addition to dienes take place more readily and at the faster rate. Third, Diels-Alder reaction. 4 plus 2 cycloaddition. This is one of the most important reaction of conjugated dienes. It involves an addition reaction between a conjugated dienes and a compound containing a double bond called a dienophile, which means diene loving, to form a 6-membered ring. Since the reaction involves the addition of a 4-electron system to a 2-pi electron system and leads to the formation of a cyclic product, it is often referred to as cycloaddition reaction. The product formed is often called a Diels-Alder adducts. The simplest example of Diels-Alder reaction is that between 1,3-butadiene and ethylene. But the reaction takes place very slowly and in low yields, that is 20%. The reaction takes place in a concerted single-step mechanism. during which C1 and C4 of the conjugated diene system get attached to the doubly bonded carbon of dienophile. As a result, the two new bonds are formed at a cost of two pi bonds of the diene and dienophile, as is clear from the above example. Diels-Alder reaction takes place very readily when substituted alkenes containing electron withdrawing groups are used as dienophiles. For example, first, the reaction between 1,3-butadiene and acrolein dienophile takes place 373 Kelvin to form the adduct in quantitative yield. Second, malic anhydride dienophile reacts readily with 1,3-butadiene at room temperature to give quantitative yield of adducts. Factors which favors the reaction. It was originally stated by Alder that the reaction favored by the following factors. First, presence of electron withdrawing groups. In the dienophile, the favorable effect of electron withdrawing group in the dienophile is very clear from the examples given above. It has been seen that acrolein, which contains a carbonyl group which is electron withdrawing, and malic anhydride, which has two carbonyl groups adjacent to the carbon-carbon double bond, undergo Diels-Alder reaction in quantitative yields under mild conditions. Second, presence of electron releasing group in the diene 2,3-methyl 1,3-butadiene affords an important example of a diene to demonstrate the favorable effect of electron releasing group in the diene. This compound containing two methyl groups which are electron releasing is about 5 times more reactive in Diels-Alder reaction than 1,3-butadiene. For example, 2,3-dimethyl 1,3-butadiene reacts with acrolein in quantitative yield at only 303 Kelvin. As a result, this 1,3-butadiene reacts with acrolein in quantitative yields only at 373 Kelvin. It has now been found that even if the locations of the electron withdrawing and electron releasing groups in the dienophile and diene are interchanged, the yields of the adducts remains unchanged. In other words, dienes having electron withdrawing groups would undergo the reaction readily with dienophiles having electron releasing groups. Stereochemistry of Diels-Alder's reaction. The Diels-Alder reaction is highly stereospecific. The most important aspects of this stereochemistry are as follows. First, S-cis conformation of diene. The dienes undergoing the reaction must be in the S-cis conformation rather than S-trans conformation. This is because only the S-cis conformation allow the ends of the conjugated system to reach the doubly bonded carbons of the dienophile. Note, 1,3-butadiene can have two possible planar conformations designed as S-cis and S-trans as shown below. Strictly speaking, these do not represent the true cis and trans formations. This is because the S-cis and S-trans conformations can be interconverted by rotation around the single bond. That is why the prefix S is used before the notations cis and trans, which signifies the isomerism with respect to single bond. Second, occurrence of syn addition. The reaction takes place by syn addition of the diene to the dienophile, and the conformation of the dienophile is retained in adducts as illustrated below. Synthetic utility of Diels-Alder reaction. The synthetic utility of the reaction lies in the fact that can be used in the preparation of many cyclic compounds, which would be difficult to prepare by other means. A prominent feature of the reaction is that it is extremely easy to carry out. In most cases, the reaction is brought about by merely heating the reactants together with or without a solvent. 4. Polymerization reaction. Conjugated dienes have a strong tendency to undergo free radical polymerization to form useful high molecular weight polymers. First, polymerization of 1,3-butadiene. Peroxides induced polymerization of 1,3-butadiene gives to polybutadiene. The formation of polybutadiene involves prominently 1,4 free radical addition of butadiene to each other so that the product obtained still contains a double bond for each butadiene unit. Second, polymerization of 2-methyl 1,3-butadiene. The free radical polymerization of 2-methyl 1,3-butadiene or isoprene gives polyisoprene, which resembles natural rubber. Thank you.